But yeah, so the focus of today's session is about PV hot water, which is part of our IEA Solar Heating and Cooling Task 69. It's one of our subtasks. And I just wanted to do a small little introduction about the solar heating and cooling program. I don't know if maybe some of you guys already know about this, but it's a program that's been going on for how many years, Ken? How long has the SHC been? 44 years. Yeah. And then, of course, there are a bunch of countries around the world. There's a map of all the countries that are involved and a few other participating organizations where people can take part in these tasks, like this task 69. We would welcome you guys all to join this task as well on solar hot water. If you want to join, you just got to make sure you're from a member country. Australia is a member for at least another year, hopefully longer than that. And you're welcome to join the task for sure, which is about halfway through our task, actually. If you want to learn more, there's a few links there. And then Solar Academy is something that the SHC puts on. There's several of these per year. And so they're kind of mostly webinars these days. And usually there's the 2 sessions to try to get both hemispheres, or both the eastern and western hemisphere of the globe. And they're pretty good. There's all different trainings and topics, usually aligned with the tasks that are ongoing. I want to save some time. So if you want more information about that, there's some websites there, and I'll try to share these slides with the conference. Another thing that's put out by the SHC is the Solar Heat Worldwide report. I don't know if anybody's seen that, but it's got a lot of good statistics from around the world of all the different solar heating and cooling technologies and how much installed capacity there is in different parts of the world. And I guess part of our task is going to feed a little bit into that as well. So task 69. So it's solar hot water for 2030. It's like I said, it's about halfway through its life. So it's a 3-year task. And it's basically looking at 2 technologies: thermosiphon systems, which have been around a long time and been providing hot water for people's houses for a long time. Whenever PV was $10 a watt, $100 a watt, solar thermal hot water was actually quite viable, and a lot of people installed it in Australia, especially. And it was the vanguard, I guess, of something you could, harvest solar energy on your own house, and lots of installed capacity before PV ever came on the scene. But we also are looking at PV hot water, which is now, instead of being a ridiculous idea to take your $100 a watt and turn it into low-grade water, is now becoming kind of economically viable with the huge drop in price of PV. And then, of course, if you think you can convert electricity through a heat pump into 3 units of 1 unit of electricity gets you 3 units of heat, then it's actually pretty comparable in terms of the overall efficiency as well. So there's some interesting things in there comparing the 2 technologies, looking at what's next for the 2 technologies. So of course, there's a lot of smarts that are coming around, and everything's getting connected to Wi-Fi, and you can really optimize the systems. So it's also a lot of opportunities for manufacturers to get in this space and come up with new products. So I think I already said that, but the one thing that unites the 2 technologies is they both have very few moving parts. PV hot water systems and thermosiphons, they don't require, too much mechanical parts that can fail. I'm a mechanical engineer by training, but I know those are the most likely to fail. And they're both pretty low cost and reliable. They can be pretty reliable and affordable. So there's some uniting factors there. So in terms of what we've been up to recently, we've put out some surveys. I'm sure some of you may have, I heard somebody had received and filled in the surveys, but we could probably still use some more responses on those surveys. I think we ended up with something like 42 responses or 44 responses on the PV hot water survey, so we could use a few more responses there. We've got some experimental test beds ongoing, one of which is comparing thermosiphons to PV hot water systems side by side in Namibia. So we're going to have some good data out of that. We already have some data from the surveys. And so we're just at the time where we got a lot of nice collected information, but we need to turn it into reports and some outputs. So I guess that's where our task is at now. Okay, so for subtask C and probably the kind of interesting stuff for today, I just wanted to set the stage a little bit. The cost of PV is much less than $1 per watt in most places now installed. In most places where there is a lot of PV installed, you don't really get much for selling it back to the grid. Okay, so there's some it's a victim of its own success, I guess, in that there's so much PV on the grid now, and especially at that middle part of the day, we need to do something with that electricity. All right, and now everyone knows if we're going to try to get to net zero, we need storage. And what do we have? Storage already in solar hot water tanks. It's a massive amount of storage. Very, very simple calculation there in the bottom row. There's something on the order of 1 billion households in the world, 8 billion population. And, I figure most of them have some amount of storage, thermal storage. So you can plus or minus that a little bit. And then probably each hot water tank is about 10 kilowatt hours. So there's 10 billion kilowatt hours in the world of storage capacity that's probably mostly already there, ready to go. And it's something that we need really bad, and you just have to find a way to utilize that. Right? And that's a huge number, 10 billion kilowatt hours. And so I think we can do something with that. Of course, it's only one way. You can only take excess electricity and put it in there, but it allows you to dramatically increase your penetration of renewables. Because of that storage without wasting the electricity. So anyway, that's one thing to set the stage. And the other thing is we cannot afford to forget about solar or about hot water because it's a big piece of the demand in most places. And in some countries, it's up to 50% of the household energy consumption. So it's something we can't forget about. So we gotta keep evolving the technology and keep trying to get solar energy into the technology. All right, so this session today is mostly for our subtask C, but it also fulfills one of our other subtasks, which is to provide trainings and workshops and stuff as well. Okay, I think that's all I wanted to say. I'll turn it over to Baran, and hopefully we can switch the camera on to Baran. Okay. Am I sharing?
Yeah.
Am I sharing onto? No, sorry. Did you make it bigger screen? Bit tricky to do these hybrid meetings.
We should actually should start public. There are other options.
Yeah, that better? Yeah. Yes. Is the camera on you? Yeah,
I'm not sure. The camera.
It's working.
Yes. Yeah, it's working. Yes. Okay, great. Thank you for the introduction, Rob. Welcome, everyone. I'm very excited to present this session today. Myself and colleague Dean will be presenting some new advancements in the use of PV electricity for water heating across different projects based in Australia. So the first project that I'll be talking about is called Solar Shift. And as the name suggests, we're trying to shift for the solar periods. And this project is sponsored by Race for 2030 program. We're collaborating with this Task 69. And our research team briefly, myself, David Salazar, Hussein Saberi, Anna Bruce, and Alistair Sproul. Alistair is also here with us in the room. And we have the project partners, Endeavour Energy and Ausgrid. These two partners are the distribution network service providers from New South Wales. We have Solar Analytics, a smart monitoring, smart home energy management system company. We have the New South Wales Office of Energy and Climate Change, Energy Smart Water, and as I mentioned, the IEA SHC. So what is the motivation for the project? Basically, as also mentioned, residential water heating takes up quite a bit of energy in terms of percentage. In Australia, we estimate around 1/3, may change from different state to state. And most of these systems are actually powered by electricity. In Victoria, we know it's not the case with gas, but that's going to be the truth of the past with some of the new incentives coming for the heat pumps. But overall, around Australia, we're talking about 52% of electric water heating systems. And again, depends on the state, but there is a significant chunk of these systems are actually controlled by network operators, such as distribution network service providers. And there's also some change in this space as well, as I will mention. So we estimate around 25 gigawatt hours of electric demand in national electricity market just from water heating. So it's quite significant. The second motivation, of course, this figure is probably one of the most used figures in this conference, the penetration of solar systems for households from the APVI website. We all know how significant it is in the residential space. We are already past the 1/3 ratio, more than 1/3 of households in Australia. And in some states, this is more than 45%, as you can see. So it's all well with the solar systems installations, but we also have some challenges with the integration of this much solar, especially in the middle of the day when there is so much generation and there is not much demand, especially from the residential households as people are working. So what results in this is this famous duck curve, the most famous animal of the renewable energy industry in the last 10 years or so, slowly became more in popularity. So as we are maybe familiar with the duck curve, the demand is basically in the middle of the day going lower and lower and lower. And as the duck gains more weight, there is more problem for the network because we don't have enough demand. We have soaring levels of solar. What happens is the voltage levels goes up, especially in the feeder level or low voltage transformer level. When voltage level goes up, what happens? It may trip the inverters, the solar system components, so you might actually stop generating, or it may also increase your electricity bills, and in some cases may damage your appliances and stuff. So these are all significant problems that we want to deal with. And the third piece of the puzzle is an announcement earlier this year from Australian Energy Market Commission that by 2030, all households will have smart meters. Now we'll see the implementation phase of this, but we already see in Victoria the distribution of is quite, and this is going to be NEM-wide and Swiss-wide as well moving forward. So combining these three pieces together is the formula for this solar shift. So electric water heating system, a household with a solar PV, and a smart metering device. But our focus in this project is actually not on a specific individual household level, but we are going to be looking at things at a more aggregated network level, especially at the distribution network level. we have done a project previously trying to develop some smart energy management algorithms for individual households. In this project, we're basically looking at systems controlled by the NSPs or controlled in large numbers. So this is, in summary, the project. Now, in this presentation, I won't be going into detail with modeling findings. We have another session for this Thursday afternoon if you're interested. And instead, I will try to cover some different range of topics. Some technical, some regulatory, a little bit of what's going to happen in the future. So we'll be covering a few different things. But to start with, I would like to present you for the modeling side of things. We basically assuming different behavior of the households because there is very limited amount of measurements that are actually measuring the hot water flow. So this is a very specific tool that requires flow meters. We only have electricity data. So these are different water draw profiles we're assuming for our study. And you can see it represents different household behaviors. Some are morning and evening, some consume hot water throughout the day, some actually come home late and have late showers, etc. So there are different types that we're considering. I will present to you a few different control loads cases here that was common in the network, and we're now seeing new things come up. So bear in mind these abbreviations because we'll see them later on. General supply, this is a supply that is on 24/7. You have power at all times. Control load 1, this is a traditional way the NSPs control the hot water tanks, as you might remember, or maybe you're see already on one of them. Hot water tanks come after 10 p.m. up to 7 a.m. in a staged and randomized way. Control load 2 is an expanded window. Now you have almost 24/7 except the seasonal peak period. So your hot water circuit will be on except say 3 p.m. to 8 p.m. which is the peak demands for the network. Control load 3. Now this is a new version where you would add a solar period like 9 a.m. to 3 p.m. on top of the control load 1 window. So this is some DNSP's new version of implementing this solar sort window. We're also looking at the control from an only solar point of view. So what would happen? Hot water tanks only heat up during the solar window, so you wouldn't have any more. And finally, Osgrid's implementation. This was close collaborator in the project as well. They're applying the solar sort window seasonally, so they change that solar sort, not on fixed time period. Anyways, too much talking. So I will show you a few results here. And the first one is the emissions that we get and the percentage of solar soaking for the typical resistive heaters. And on the y-axis for the first plot, you see the annual accumulated emissions equivalent of tons per CO2. And on the x-axis, these different control strategies that I've described to you: general supply, control 1, control 2, etc. And what we can see basically is intuitively, during the only solar option, you have much less emissions. And by the way, these simulations don't assume solar salt potential at individual level. We're assuming all water tanks soak up electricity from the network. So you're not doing the behind-the-meter thing. So we're basically calculating emissions on a network level. We're using a tool called Remit, an open source tool developed by our team members. And it gets hourly average emission intensity for each network and user. So different emissions intensity with different control strategies. And you can see the fraction of solar consumption, what percentage of hot water electric consumption comes from solar on the right axis. So yeah, you can see that control load 3 and the Osgrid solar soak is actually a lot more solar percentage than the traditional one, also general supply as well. Now, this plot will show the annual energy consumption by different control load strategies. On the left, you have the resistive type, and on the right, you have the heat pump. So we'd like to just highlight that on the left plot, we actually have a bit of a hiccup on the axis. It should have started from 0, but it's starting at 1,000. So just bear that in mind, because that red horizontal line represents the amount of useful hot water energy. So this is what is being consumed in the household. In contrast, those bar plots shows how much energy we have to actually produce to be able to provide that useful energy. So the difference is the heat losses. And for resistive systems, this is sometimes 1/3 and 1/4 of the energy that we use goes as a heat loss. This is for Sydney. For different cities, as I said, we'll present more results on Thursday. And the heat pump, you can see on the dashed line, the amount of annual energy is by those black lines. So we're basically operating at a COP of 2.5 to 3. So it is a obvious advantage of using heat pumps. And one last point here is that dashed black line is showing basically, compared to control load 1, which most systems were on, what happens to the annual energy consumption to the water meters when they change from that control load 1 to control load 2, or control load 1 to the general supply, etc. So an important statistic here is this average 4.27% from changing from control load 1, which is the base case, to control load 1 plus the solar source. So this is where the networks are going. They want to maintain overnight heating plus add a daytime heating period. When we change that control period between two, the electricity consumption by default changes on average 4.2%. That means the bills may increase, right? And this actually ranges within 3 to 8% depending on the system. So this is an important point that will come handy later on. Okay, one last slide here is the emissions comparing heat pump and resistive immersive for different cities. And again, you're looking at the emissions intensity for each different state and region for these capital cities. And we've assumed one typical water draw profile for these plots. And this is basically to show you how does the water heating emissions change across different capital cities, as well as the difference between heat pumps and resistive immersive heaters. Okay, so much for the modeling. Now I would like to show you a real-world trial that we are running in collaboration with the industry partner. This is let's say a sister project that we're working with, and we have around 20,000 participants in this trial. And basically now on this shaded gray area, you see the overnight heating, and with the different colors, you see different groups. There are 10 different groups in this spot that are coming online. And then there's a little bit of a relative peak, and they come down. So, and on the right side, you can see the x-axis, it's a little bit small, but daytime. That's the solar source window. So you can see those 10 groups coming online in a randomized way, around half an hour to hour randomization. So basically, we've tried different strategies, and sometimes the communications didn't work properly. And when that happens, all the systems come online at once, and you have a local peak demand, which is not desirable. But when you get the randomization work, you actually reduce the peak demand by 40%. So in those plots, we're looking around 15 to 25 megawatts of controlled electric water demand. And this is from a trial in South Australia. So far, we've only tried simple and static control strategies. So these systems come online, same group comes online at the same time every day. But we are developing some more dynamic strategies as we go further along. An important outcome from this is around 40 to 50% of daily hot water demand is shifted to daytime, even if you implement a very simple strategy by basically turning the hot water systems during the day, which is, I think, quite a significant achievement. But there's one caveat here, as I said, the annual energy consumption of hot waters are increasing by on average 4% with this strategy. So yeah, and it's actually within the range of 3 to 8% that increase. So where does the future of control load? And I would like to summarize a few updates on the control load. Basically, as householders, we can go and change our water heating technology options without notifying the DNSP or retail. We have the freedom to do so. If you are on a control load previously, if you'd like to go and disconnect your control load, there are some fees associated with it, around $150 to $200. So what happens is most households actually avoid these costs by simply getting a new hot water system, but they're not disconnecting the control load. So that circuit becomes inactive. There is zero load on the circuit, but based on your DNSP and based on your state, you may end up paying daily connection fee charge for this control load. So I'm not sure how long it's going to take to pay off that $150, but this is what we see. In fact, in South Australia, around 20 to 25% of the existing controller fleet is now inactive. So this is quite significant. In New South Wales, we're looking around 100,000 households from Endeavour Network and around 500,000 from Ausgrid. Around 15 to 20% of the control can become inactive in the last 5 years. Yes.
The control loads, just the old-fashioned set to the old-fashioned.
The old fashions are ripple control, most of them. Some of them are mechanical control in different states. Yeah. And also we do the questions at the end. Is that the format? Yeah. In Queensland, after having different interviews with the NSPs and installers, what we found out that around 1 in 3 installers basically go and install the system. They also end up changing that control load to the general supply, and they plug it in. So what does that tell us? Basically, we're losing our control load speeds. Is this a good thing? Is it a bad thing? I've released a magazine article discussing this. If you like to go and, if you like, you can go and read it. Some different relative advantages and disadvantages to this. But there's a key message here. There's a reason why people are moving away from control load, and I'll show you why in a second. So these are new distribution network service provider tariffs for the control load. This is from Ausgrid solar stock option. Navid here can vouch for this. Yeah. We have Endeavour Energy's off-peak plus tariff from Victoria, DNSP, City Power, United Energy, Power Core. They also have a different 24/7 time of use control load. So the control load is actually on all the time, but there are different rates to use this circuit. And they actually have $0 per network charge for most of the time during the solar periods for this control load. Maybe you might have heard Sapiens Solar Sponge, where it's cheaper during the solar window to use control load. Again, they've changed the control load to make it available 24/7. Energy Queensland is also doing some new trials for the solar soak. So the key message is there are new tariffs that offer cheaper network rates during solar soak period by the NSPs. But I'm not sure if this is the same thing from the retailers. We're not seeing the same level of progress, let's say. And here is an analysis. What we're looking at, around 1,000 households across different states, and we are calculating the distribution of savings that can be achieved by an aggregator or retailer simply by shifting from the control load 1 period to control load 3 period. And control load 3 meaning that traditional control load 1 plus the solar soak period. So you're basically doing wholesale arbitrage, because during the daytime, wholesale prices are much cheaper. So you can see the distribution of savings across different states at a per household level. If you were to change from a previous control load 1 to only solar, so if these retailers started operating them only during solar period, the savings even increase. You can see it on average more than $100 per household per benefit per year that retailers can gain. So what is the key message here? As we discussed, electricity prices have recently increased yet again, but the feed-in tariffs didn't follow that same trend. So the motivation to use self-consumed solar is much higher now. And DNSPs have started to offer new network tariffs to encourage consumption during the solar surge periods. But what we need to do is we need to come up with new and innovative retailer tariffs to pass these savings to households in order to maintain a central control and orchestration for hot water flexible demand. Now we can discuss if this is a desirable thing or not, but households are moving from control load because it financially doesn't make sense for them anymore unless you find the right value proposition. Okay, a few more slides and we're done. So regarding heat pumps, we've heard this talk earlier from Solar Victoria about their incentives. We have different incentives from different states, like New South Wales, we have energy efficiency scheme or peak demand reduction scheme. In Queensland, we have climate smart energy savings scheme. In ACT as well. So what these schemes are doing basically is subsidizing more efficient electric water heating technologies, such as heat pump, as well as some solar thermal technologies as well. There are some quality and customer satisfaction concerns because there are a lot of cheap heat pump sales out there apparently, and we've got some of these complaints already. So this is something to look at. But as I heard from the previous talk, heat pump sales have increased 500% to previous years. So this is quite significant. And now here's another question that we discussed during the panel session. What happens to flexible demand if all of our existing resistance switches to heat pumps? And so this might be an ideal thing. You solve the problem from the beginning because now you have much less energy than your daily outdoor energy needs, 1/3. But now you only have 1/3 of flexible demand. So what do you think? This is important point, and some DNSPs have different views on this. One more thing to mention here is heat pump manufacturers and installers recommend installing these units on the general supply rather than the control load circuit, where actually the essential control can happen because they want an uninterrupted operation. And even Solar Victoria now, they basically mandating integrated timers with heat pumps, so which is a promising thing. But again, these will be all on the general supply. Just one final plot here to show the difference between an immersive resistive heater and a heat pump operation. At the top, you see a resistive heater. It's more intermittent. It can operate more intermittent, around 3.2 kilowatts the size. And on the bottom, you can see the heat pumps and around 800 watts. And you can see that it requires long, uninterrupted operation. And its rating also changes depending on the time. So one last piece of the project is the consumer engagement. So we are collaborating with Solar Analytics, they're based in Sydney, to develop an online tool, a Solar Shift online tool, to offer customers different options when they want to electrify their household. So you could only go with a solar PV option. You can maybe buy solar and battery, or you could also choose solar with different hardware technologies. So I'm trying to provide them estimated savings, what are the relative advantages and disadvantages in these technologies. And so far, we've had 60,000 inquiries and use of this tool, so that's quite promising. And as we collaborate more, we're going to integrate different water heating options. So far, we mostly focused on heat pump and resistive systems. With that in mind, I would like to thank you for your attention. And once again, thanks to Race for 2030 program for sponsoring our research. And our research is also supported by the ACAP, Australian Centre for Advanced Photovoltaics, and receiving funding from the arena. I appreciate your attention. Thank you.
I think you'll, yeah, well, question.
Yeah, okay.
A couple of minutes for questions.
Yeah.
Simply heat loss, simply by how would you calculate the heat loss?
The heat loss, we use the Transys software, and yeah, those are the results we obtained for a 315-liter tank, 3.6 kilowatts, and we basically looked at different manufacturers, or ducts, and the U value that's even with one of those data sheets. So that's the but as I said, the heat loss around 1/3 to 1/4. So that plot was a bit achieved. I'm not sure if it's,
Did you use the stratified tank or you snack?
yes, it's stratified tank. Yeah.
Stratum standards allow particular housing. So the more efficient you want, the less often you use, the more static loss. It's, pretty much from the manufacturers like to use their tanks and insulate better. I've had to go a few companies over the years to make it like into change.
Things that's 5%.
Yeah, the Australian standards regulated.
But I'm sure
Systemic shock.
there are some advanced water heaters out there, like companies out there, and most are much smaller for them because they're much better insulated than the average tanks. But
With the trial you did you have customers running up hot water, do you know?
yes, so there were 4 instances that they complained to the retailer that they ran out of hot water. The reasons were mostly about communication issues. So these controls basically done central, like API, communicates to the smart meter and then to turn the relay on and off. Then we have to come up with safeguard mechanisms and communication fail. And another funny thing is, as you mentioned, some people actually have the real floor heating on the controller. And during daytime, they noticed that the house was getting much warmer and they make that for the video. So I don't know what they need to do. Maybe they want to come out of the control if they don't want to get.
You mentioned that you model a 315 litre tank.
Yes,
It seems fairly large compared to the average household. Well,
yes. So David, who's working on this project with me, he has basically made a sensitivity analysis looking at different size tanks from smaller ones to even larger ones. And we got like many results based on different tank size, daily hot water usage, hot water draw profiles, etc. So they'll be presenting on Thursday afternoon. Yeah. Great.
you'll present.
Yeah, he can't be here unfortunately, so he can start. Thanks everyone. And Dean.
Thank you.
You did it. Oh, shoot, the screen.
Right, so I'm up next. Thank you all for coming. I'm here amongst some wonderful friends, which is great to see, and some new people as well. I am going to present a little bit today about PV water heating. I've just finished a PhD. Gary at the back there is my supervisor, and bless him that he's put up with me for 3.5 years or 4 years. And it's only a couple of days ago that I actually got finally through. So hence why they changed my name to Doctor a couple of days ago. But anyway, I didn't want to report. But anyway, I do also, I'm happy to admit that I work for Ream Australia. So I've been an R&D manager there for about 10 years. And so for the past 4 or 5 years, I've been very much part-time doing a PhD full-time. I'm also a rep of the Clean Energy Council of Australia, and Ken's the chair of CS28, and I see some other CS28 wonderful friends here as well. So it's a wonderful community to be in. I'm also the subtask leader of this Task 69 for PV water heating. So today I'm going to talk about the potential of PV water heating. Really, it comes down to a lot of research that I did in my PhD. And I looked at both immersion element water heating and heat pumps technologies, and you'll see in a few different ways to try and maximise rooftop PV, but also to stabilise the electrical network, and you see how it went and other things. So, I'll pick up on that. So the data presented today will be a presentation of Sydney and Adelaide, Australia. So Sydney was part of, there was a data set in Sydney that I used, and that was the first results you'll see. The second lot was in Adelaide, and predominantly that was on the South Australian Power Network. The main reason why I chose the SAPN network was that that is the most saturated PV market per capita anywhere in the world. So it really is seen as a leader, and Victoria's not far behind it, but basically a leader. If you can show that you can do these wonderful things in those kind of things, it really becomes a pilot plant for what's available elsewhere. So my PhD was decentralized thermal storage to stabilize electrical distribution networks. When we talk about a snapshot of water heating counts for about 25% of the household energy consumption. That's give or take, but on average, it's about it. So it is a significant load on the house. There's about 10.9 million homes in Australia, and in that sense, we consume about 16.7 terawatt hours of thermal energy per year. To put that in perspective, that's about 10% of the national electrical consumption. Now, not all of those are on electric storage. There's a lot of them in gas in Victoria, but if we shift the whole lot over, you can see it's going to be massive sort of thing. So obviously we need to get efficiencies out of it. So we can't just put 10% straight on or a huge increase in electrical and thing. So we're going to have to get some heat pumps and so forth to get some efficiencies out of it. But you'll see heat pumps have got their pros and cons, and there's probably a mix of technologies you're going to need in the end. The current fleet in Australia storage heaters represent around about 0.9 gigawatts controllable load. So right now today, it's a lot of water heaters. We said every single water heater is stopped today about 30 or 40%. Obviously, if we control the whole lot, we have 0.8 gigawatts controllable load, and that is the sizable controllable load. The trouble is communication, controlling in such a way that everyone gets hot showers, no one runs out of hot water, everything's still going to be working fine. And in the end, you've got to say, what do consumers want? You want to turn the hot tap on, they don't want to know what you're doing. Beautiful things about water heating is with storage, we can turn them on and off relatively quickly, and they're fairly flexible, and people are still happy with us doing that. So heat pumps sales have been exponentially increasing, and it's mainly driven by multiple government rebate schemes. But also, I think considerably, people have really started to take an interest in their environmental footprints and also costs and emissions and so forth. So there really is a synergy here where you can sort of have your cake and eat it at the same time. So PV water heating really is a realistic opportunity. We can use PV. Historically, it has been because it's black water, it's like the devil's wood. You see, it's a wonderful thing to just make hot water. That's where it's all has been wonderful for years, and I want to a lot of our forebears have such a great technology that I really do think still has a future. That's why in subtask B, task 69, we're looking at thermosiphons. So thermosiphon water heating will definitely have a future, particularly in developing countries and so forth. But ultimately, as more people becomes available, this kind of technology of people can definitely help. So my first bit of research was really to look at, well, let's look at the standing storage electric water heater. Just say, take it off control load, just put it in the English tank. Let's see what we can get. So this is in Sydney, this data set. And really it sort of becomes, well, you can only get about 12.7% of your hot water energy from your own PV. And you have to draw 2.3 megawatt hours from the grid for that. So it's not an ideal thing. Ultimately, that's because the time of day that people are using hot water doesn't align with the time of day the sun shines. Unfortunately, you turn the hot tap on, draws cold water in, thermostat goes on, and draws energy from the grid. So you've got to get smart with the controls. If you push it, I won't read the memo, so all the hard to stick around. But basically, if you push it to the limit where you've got it, now let's put 2 zones, 2 zones of heating. So I've reduced my heat loss because I've only heated half the tank from the grid, and the rest of it is from PV. So hopefully that's okay. If you live in I know you said And I'll fight for it, I promise you. But, the laws do this, it's a long run. So, happy to have you. Yes. But anyway, that's where we are. But you can see here just by control and a bit of design, right? Then you can put it to that was a small payment. That was only a 3.6 kilowatt hour, sorry, kilowatt peak PV rate. Back then that was big, but now that's relatively small. It just shows you can have a massive improvement with not very much, really focused down. You can push it to only 0.4 megawatt hours of energy from the grid. Everyone's still having a hot shower, all the Legionella requirements were met, emergency heating, everything was still met. Let's compare that to heat pumps. So heat pumps, if you just took a heat pump today and you ran that same heat pump, exactly the same conditions, you could get around about 21% PV contribution during about 0.9 megawatt hours from the grid. But here's the real kicker, and this is why I was a massive advocate for put it out. Just put a simple little timer, right? A simple timer on the heat pump, and look what it can do. You can push it from only 21% from that small PV to 74%. But interestingly, you can see the grid draw is pretty much comparable now between the two technologies, between what is storage electric at 0.4 megawatt hours per year on the grid to about 0.3 megawatt hours on the grid. But I would stress again, the timer is only so price. It's either less, and that's basically free with controls and so forth. And look at the massive improvement you can have. So, what a getting picture in. Barron's touched this quite a lot, so I won't draw on it too much. But if you look at the traditional off-deck water heater, that's the two blue bars at the end of the screen. So that's like the start of the day. And you can see it works historically quite well for us because it doesn't align with the peak loads. So the peak loads are still unaffected by water heating, so we're still okay with those things there. However, if you put a whole heat without time, you can go and install one of these. Here's the training. Because unfortunately, when people are turning hot taps on, happens in the morning showers and then afternoon when they get home, and those luminaires now are when the heat pump turns on over the whole year. So this is how much energy is consumed. Now, sure, if you look at the y-axis scales, they're different because you've got COP of the heat pump. But unfortunately, what you've done is you've actually increased the people by incentivising heat pump. So we've now created a bit of a vicious problem where we're trying to reduce technologies, but incentivising more by using this technology without timers, we've now caused this problem. So that's just why in this state here that's done with this heat pump, this was done in South Australia. Split Stephen had the same kind of technology and so forth here. And what the map on the left sort of shows you is that we had, unfortunately, a peak period at the top, which where most of the years, the middle of the year was the biggest thermal load consumption, and this is looking at how much wind there was. So this was a much larger PV array. This was a 6.6 kilowatt peak PV array at this stage. And you can see here by just simply putting a timer in it, it reduced your grid consumption by 81%. That simple little $5 timer and so forth was. Now we actually did in this project further a techno-intelligent test bank, and that's what the paper was produced there. To putting it up against machine learning, battery charge profiles, and a whole heap of different heat pump control algorithms, including variable capacity heat pumps, that depends on the new ways on how to test them and model them. But basically, you can sort of see that in the end, it became your simple heat pump with the $5 timer, which is so cheap to sort of produce, was the cheapest option for you over the life cycle of the total investment. You put a big PV on, put a standard heat pump with a timer on it, and that was your cheapest option for the total energy consumption in the house over 10 years. Admittedly, variable capacity heat pump got close, but it's a cost of $500 or so to put a lot of technologies into it. So it wasn't quite there. Batteries was hard to actually find a payback. Just on touching on that a bit more, remember the speed heat pump with intelligent battery charging and so forth. We ran a model here. You can see that was a transit simulation, but a spike and a plugging to actually control and correct the speed. So what the pipe and plugging do is it would automatically set for the optimal speed that the compressors would run to try to actually push it to its limit for how I could actually get a sub time step regression analysis that actually determined what that optimum PV pressure speed was. But as I said, in the end, the inclusion of the battery didn't have a large impact on the heat pump grid consumption. If you can get so much of your benefit simply by putting a timer on it, there's not much left for what the battery can deliver. So if you're going to choose to put a battery in your house, it's really independent of your heat pump selection to put the timer. Heat pump controls timer variable speeds were effective in matching the PV generator. So we're pretty good. You could ramp the speed up and down. But you've got to remember that PV can change its available energy to PV can change fairly rapidly. Someone turns toast on or whatever else, the amount of energy goes up and down. Heat pumps struggle to respond really quickly to those kind of things. They can literally ramp the speeds up and down and so forth, but they can't do it in the sub-second sort of periods. Variable capacity heat pumps would further reduce the grid consumption by about 28%. And as I said, they were close, but they couldn't quite get there to the light. They had a slightly higher lifetime cost. I would definitely watch that technology. I know it's running is stable, and if we can just drive that cost down a bit more for the variable speed control, then I definitely see there's a chance here because it is a significant reduction of energy, another 28% if I get it, but it's just not cost effective at the moment. So batteries could reduce the net household, just the whole household energy consumption by 72 to 82%, 77 to 82%. So you can see there's a massive energy saving for the battery. I've got it at home because I wanted to do this home and see how I found simple kind of things. There's a huge benefit there, but it's a huge capital, and that's just where it's make viable things. So even though we did machine learning, when you actually beautiful thing about simulations, you can know what your perfect charge cycle is, so that you can test your machine learning charge cycles to say how close it is. Believe it or not, we've got to 99% of the potential savings. So we can pull back about $581 a year, but the payback was about 12.5 years. So if you're trying to get a 10-year life cycle, quite get payback battery contained. So the optimum consumption is this large PV array, heat pump with a simple timer, and you could lower your 10-year energy cost by 27% just by putting those few things together. And it had a 7.8%. Now, I must stress that 7.8 payback period was calculated. This is an international paper that was produced here, so we didn't put rebates in. So there was no rebates of PV panels, there's no rebate for heat pumps or anything like this. This was just the set prices of what they are, and you could get about 7.8 year payment. So if you get the rebates and so forth, then that's going to flow. All right. So looking at demand response, I'm not going to go through the ins and outs of what the graphs are, but effectively, so same as what I'm trying to do, but I suppose I went into the minute where I was responding to real-time grid prices and FCAT things like went into frequency control with water heating. So if I frequency control should be a bit to get my head around how can I affect the frequency of the grid? Well, if I've got a massive load and I suddenly turn that load off, the generators will want to speed up because you've taken the load of the generator, so the frequency will go up. The same is true the other one. If for whatever reason the generators start going faster and I want to slow them down, I turn the big load on, I'll pull it down so I can have a frequency control. And the beautiful thing about immersion elements is it's a big load. It's a 3.0, we have 10 gigawatt controllable load, so I can have a relatively fast response, and I can have a big impact on it. So the existing studies that identify the potential, however, the detailed design and controls for lack of power is practically. So we have to come up with new business models because as was touched on before. The problem is you have to somehow pass the incentive on to the consumer in the end, and there's a few steps in the pie to get there. But ultimately, if you look at some of the nitty-gritties of it, this was just one day of one of the simulators I ran over the whole year, and you can see the blue bar at the end is a typical off-peak control load plant water handler. The yellow line is low, and it charges up at the end of the day. That's what it is. The black line down is the real-time price by the spot price. That one. And you can see here that with the control algorithm and the slightly two-stage heat water heaters and so forth, then as the price starts to fall at the start of the day, and the state of charge is low, the orange one now, it says good time to buy, so start buying, and then the price gets too high enough to buy more. So you get to track the low price is definitely buying it, right? And you can see that in the case of what the off-peak will be, this is at wholesale rate, it was $75 a megawatt hour. But if you target the cheaper times, you can get an average price of this day of $4 a megawatt hour. So you can significantly save consumers big money. Now, FCAT was the other one I mentioned on it, and on this day, you got an FCAT raise of about $2.16 and FCAT's lower, 2018. FCAT's lower is much smaller, even though it's on more often, because the price is, you know, they're going to pay much dividend $2 a watt, but because they really need the rate. But you can see that actually on that day, I was continuously, that could have responded, but I didn't. But I took a pay. So that's how this one. So that ultimately you can see on the left hand side and the right hand side with the control flow like we can have the costs. But in the end, we got to the data reverse costs. Theoretically, if the wholesale price data is passed on to you as a consumer, you get given a check at the end of the year for turning it on. So your price is still now costs and wholesale. So the key for it is two-way communication. You need to really communicate to get these to build the most out of it. You need to communicate in both ways. Where the water heater state of charge needs to be told to the aggregator, but as you know, to make sure people don't use hot water and to make sure Legionella is sorted out and everything, you've got to have some control locally as well. You've got to have it that it's autonomously looking after itself in every location. It's just getting centralized control signals. So please do this or please do that. So to stay on, let's now consider that our business is not our group, and we're not an individual household. Let's think as a whole community how we can make this work. And this is really a bit of a fall rate, falling a bit, but I'm glad I was pushed to do it. Effectively, we need to pick the income. So that becomes how could we set up a market? And I'll then do the labour I did not too much and all that so we can start trading. You know, next door neighbours or down the street like that. There's a lot of research going into this, and they really see this is a huge way of incentivising a greater PV capability on a network or increasing hosting capacity. So really the biggest battery we've got in Australia is our humble water heaters, but we've got to all work together. It's what it comes down to. Now this one was a tricky one to model because effectively what I had going here, I had 12 interdependent transient simulations that all ran at the same time step, and they all fed themselves into a Python model that then would take information from the grid and so forth, determine who's going to go and who's not going to go, and trade energy. So it was a beat to get going, but it did work. And using this one here, we could effectively we could get the water heaters to sympathetically respond to the grid conditions. So which key then works for us? If everyone suddenly goes, prices good, all going to go up, it's a disaster. Because we all there's huge spread all over the grid. So it has to be proportionate. That if my heater's pretty low in its charge, I'll go with Paul because Paul's heater's charge higher. But if the price is really low, we're both going to get. So that's how you sort of work to say, but that's what the grid wants. If the price is really low, it wants to be low. So whatever you do, you really want a proportional response. And it's probably going to be key to making this work. But the results were without peer-to-peer energy trading across the whole fleet. Even with the best controls I just showed, we could only use about 39% of our rooftop PV down this self-consumption. But when I put peer-to-peer energy trading going on and so forth, I could push that, I could double it to, I think the number's actually here, 83%. We could push it to say across the whole network. We can self-consume 83% of all of the PV that we generate across the whole. And the key really here is to say we sort of made a cloud thing. Well, we had to make it here. The last 17% was when the grid is stressed and it wants energy. Instead of being self-consume PV, we deliberately made the decision to say, no, stop using energy, and I'm going to let the grid go. So we've reversed the duck curve to an extent with water heating to be able to say we're going to take that value out of it because we're now self-consuming so much of it. But the times where it's really peak and we have PV energy available, I'm going to let it go to the grid. I'll tell it, just be made for us. But I'm going to deliberately let it go. So it sort of works against the idea of PV self-consumption to then become, well, no, let's actually try to help the grid and get some money at the same time for doing it. So the real kicker was that when you unlock that peer anti-trading, you can increase the savings by about 31%. So the average consumer goes up by 31% by just allowing that trading to happen. Now, how could that happen? How could we get a market to do that? Well, and policies, everything. There's lots of things to do it, but it does show that there really is a holy grail. Well, I can be careful, but it is one of those things that say that ultimately the tide, and it must have been $300 per average customer. That was done at a free cutter zone. But previously, the savings of the was a wholesale retailer. So I used a relatively novel retailer it's called Westport, but I think they're great. And they effectively track the wholesale that they pass, not all of it, but they pass that tracking onto the consumer. So using that business model was what produced $300 per year average saving. They increased the saving by $300. There's a paper that's been published on that. That's been kept. So effectively what I'm saying is we need both. Let me turn them all on. We need both. Storage, electric, water heaters has a very much a pro. It's a comparably large energy draw, and normally so that's what we see. But we can really have a big impact on demand response with an online. We don't need millions to do it. We can get them it can be relatively flexible and we can modulate it to match the available PV. But I mean, albeit that all of that product does do that. I don't know whether that's the key of it really anymore. But if you're storing a little bit and Christine's exporting a little bit, in the end, balance out, it doesn't really matter, sort of thing. So we probably don't need that final thing if we think together. The real key of it is we need a very fast response. But it means that we can really play that. Now, as we retire coal plant, that everything's becoming more difficult to that's what it's going out. Ultimately, I think what Chris believe batteries will chew that up at the FS market consider drop. So I wouldn't be designing my brand water heaters and thinking that's my business model for the next 15 years. But I think demand response is probably several years ago. Times these emerging technology is relatively expensive. It's ultimately consumed more energy than heat pumps. So that is key. We don't have an energy shortage right now, but as we put those vehicles, all of those kind of things for the future, we definitely have some challenges there. And the high participation we need to realise its full potential. So we're all going to get in those to get some heat pumps. I have absolutely a huge kind of heat pumps as well. They're highly efficient. They're relatively low energy costs because of that efficiency and so forth. Low eligible bands, high ability of 100% PV operation. That's why the timer is so effective in that. The chances of having 800 watts, if not even less than that, available PV system in the middle of the day is pretty high. Chances of having 3.6 kilowatt is significantly harder to time. But that's where you're going to modulate PV on conversion, but you don't necessarily have to modulate so much. The cons are high embedded energy and capital cost, lower power drawing, lower impact on the grid when under demand response, albeit if we've got lots of them involved, we can have a big response and so forth. And the speed of the response limits the demand response impact, especially on the gas market. But again, there's lots of us, and we can really play into that demand response component. So to realise the potential of heavy water heating with regulatory support, new standards, product designs, large participation rates, and we're really going to need aggregators. How do we make a market work, and how do we pass the savings on to the consumer at the end of the day? I've spoken enough. Any questions? Can I call that time? We didn't have to. Sorry, we're going to play.
It's just wondering that demand becomes its cost.
Yeah.
Effectively, of
So
this basically assisted.
yeah, look, there is definitely. I mean, heat pumps are a mature technology. They really are. And there's heat pumps that have been installed and they're still going 10, 15, 20 years later. So, and, you know, the technology proven that heat pumps can last. I think the question also has to be, well, what can you get away with? That means the lifetime won't be a sort of thing. So there definitely is a challenge, I think, with embodied energy, for instance. You need to get that heat pump to work for many more years than immersion elements to actually get the embodied energy back out of the single thing. But I didn't really, I looked at it, said, look, the lifetime for that lifetime analysis when I was preparing the two lifetime ones, it was basically 10 years, 10 years. What's the capital return in 10 years? How can I get this full, something like that? I didn't try it 15 years for this, 2 to 12 years for this or anything like that. You want to
Very fast. It's anything else.
Yeah.
Yeah.
Yeah. I mean, in terms of the two technologies, we think heat pump versus this demand response heaters, the absolute manufacturing cost of the two, and or installed cost, if you've got about rebates, it's kind of similar. So it gives you a bit of an idea to rates. Now, the proposal that Barron's got is a wonderful one because it's not much at all. We've already got smart meters that use the existing water heaters. But much bigger application is in this much bigger fleets available. So it's a huge potential probabilities and so forth. But in terms of playing with the FTAP market, all of that spot price demand response and so forth, that two-stage water heating, all those kind of things, they're not really compatible in that sense. And this is where I'm sort of suggesting, I think ultimately in the future, we're going to need a full volume of these really high performance controllable water heaters, and we can actually do that fine adjustment to the grid, that we can do it relatively quickly and get that right. We're going to need a bulk that's maybe the cheap demand response sort of capability, and that will probably switch over time into heat pumps. And I think the natural progression is going to be that as we put bigger electrification loads like electric vehicles in the grid and so forth, we're going to need to switch more immersion element technologies into heat pumps because we're going to need to get the efficiencies in there. But ultimately, in the end, I think you're still going to need that high speed response and so forth, and the big load change of the immersion elements and so forth. But that might only be 20% of the total mix or something. Mix. Brian, do you have a question?
Yes, a couple actually.
All right.
With the timer, and you have a lot of simplicity of a solution.
Yeah.
But then I'm thinking, if the heat was simple, if you have like a data just rigid schedule period there.
Yeah.
How did you look at how that would have to be varied over a period? Because if you said something, you fix something, as you know, with the heat pump, how it operates during summer and winter, the efficiency in the requirements, you would find that you may have to actually be extending or reducing timing periods depending on what you need. And you also mentioned the fact that we may have solar, or you expect solar, and in some places you will certainly get solar much more than in other places.
Yeah.
But then of course there will be periods where you don't have it, but your unit will be on. So as much as I like the simplicity of the timer, I see the disadvantage of, well, you know, something set. So if you say, okay, I'm just gonna go 5 hours here to take advantage of sort of sponge sort of thing. But hang on, and when that might not be enough time for this unit to heat, but like 12 significant amount of other 10.
So it's a good point you mean, because heat pumps aren't just purely, okay, how much energy you just draw. Like how much thermal energy and how many hours does it need to recharge? Because we get into, well, how big is the capacity of the heat pump? Now, there's a big push in Australia to go cheaper products, small capacity. So we're down to really small compressors that can't recharge. So I think that heat pumps with timers, I put a pretty generous window in there. And sure, there's going to have to be a bit of flexibility on when they all come in, so they don't all come in the same minute sort of thing and whatever else. But I definitely think that with a decent storage capacity of around about the 300 litre again, that's what it was, you're going to have to be in that sort of range to get enough energy storage through the whole day so people don't run out of hot water. But you're going to have to take into account capacity of heat pumps, so how fast it can recharge and how long it needs through its hours of window. Because ultimately, in the end, if someone says I've run out of hot water, get me off this crazy scheme, and you've lost them. And you've lost all their mates as well. So it's so key that you don't screw one customer over. I'm sorry, there was 4 and the other one dropped, but it's just, I can't stress that enough. Anyway, I think we've got to move on and so forth.
Yeah, can we save the rest of the questions for the
Discussion.
Or yes, but let's thank our 2 speakers. I wanted to say one thing. This is all kind of Australian focused, but we also have some international visitors here. So Fan is coming from Denmark. He's going to be on the panel giving a little bit about the international perspective, and we have some Chinese visitors and many Chinese manufacturers making these sorts of products as well. But anyway, Australia is hitting this high renewable penetration before many other places around the world, and it's going to roll out to those places eventually too. I think. Love it. And then I'll let you stuff.
Yes, I'll share. So we're lucky today to have the next section is a panel session where we're going to have 4 sort of industry and government and experts on grid interaction, PV and so forth. I won't introduce them. I'll do a poor job of that, and they know themselves better than I do. But if I could ask the 4 panel members to come up here, and by all means, we'll get them to quickly introduce themselves, and then the floor is yours. If you don't jump in with questions, then I will be. So.
Yes. Yes. If you could sit where the camera can see you, that'd be great.
Now, it's a small enough room, so we're going to use the microphone.
Panel is going to say. Yeah. You're
We're finding the same industry experts and government. And government.
You were the first on one. It needs your input. I definitely think it's key. You're right.
Yeah.
Okay, so maybe start at the end. Chica's going to introduce herself, and then the others can as well. And a little bit about yourself. Interest in these people aren't necessarily all PV water heating experts, but they are phenomenal experts in what is going to be required to actually enable this kind of PV water heating to actually see its potential and demand response sort of thing. So it's all well and good, you've got a technical nerds and so forth, but without the key inputs of these kind of experts and so forth, we really won't actually get to see the benefit of. So I really thank them dearly for being wonderful friends to say yes to being here and so forth, but the floor is yours.
Thank you. My name is Ruchika Diora. I go by Chika. I work for the Center for New Energy Technologies, and we're a nonprofit organization that looks at second and third horizon gaps that are emerging in the energy transition, and we fund research collaboratively with low voltage DNSPs, universities, and government to address those. My background is in demand response, strategic marketing, and consumer engagement.
Thank you. Hi, everybody. I'm Paul Corker, I'm Executive Director of Policy Programs and Industry Development in Solar Victoria. And it's great to be here. I think during the last session, you would have heard from our CEO, so I won't try to repeat all that again for you, but some of that growth that's been talked about here by the speakers earlier has certainly been observed in our program. We offer for Victorian households who have an income of under a household income of under $210,000. We offer an additional rebate into the market of $1,000, up to $1,000 for the installation of an energy efficient hot water system. This calendar year, we've seen 99% of those go to heat pumps. So it's certainly a huge growth. So it's about 500% growth. That was actually last year. And it's what that does though is it masks the numbers. So we actually saw our hot water program, which started in 2018, be very much a poor cousin to rooftop solar. So somewhere in the order of 1,000 rebates per year through that program. That was it. Customer demand was just so low. Last year we saw 5,000, mostly in the last quarter of the financial year. This year we're on track to spend. So huge growth. That growth's been mirrored in New South Wales as well. 17,000 last year, 56,000. So huge growth in interest, and not just the rebates. It's coming and understanding what it is.
Yeah, I'm fine. I'm coming from the Technical University of Denmark. I work as a professor in the department. I've been working in this department for almost around 20 years, focusing on different solar heating technologies. So we work both on like a small solar heating system for single-family houses. We also work on large-scale solar heating plant, like solar district heating for consumers in the district, like the town. And related to PV solar heating, so we are also work on this heat storages for many years. Before I came to this group, we have a group working on heat storages for many years, headed by Simon Bobo. I think some of you will know him. And for the water tank, we are focusing on this simulations, both safety simulations and also transit modeling, this modeling of heat storages. So this is also that is relevant for PV heating. We could utilize the thermal certification in the storage to benefit from PV integration in the system. Yeah, so this is a kind of our interest in this topic. Of course, I would like to share our experience, the viewpoint from Europe on this topic. Yeah, thank you.
Hi, I'm John Tennyson. I'm probably the oldest in the group here, and kind of transitioning into a retirement phase. But at the moment, I'm providing some technical advice into the sort of enhanced system planning program that Rishi constructed with CPNet. My background is from the utility industry, so I worked in the utility industry for more than 30 years. A lot of that time here in Australia, before that in South Africa. And I guess most relevant to this is that these last several years, I was one of the sort of the founding people and working through the ARENA project edge and distributed energy market sort of trial demonstration. And then a lot of what we spoke about earlier is quite in that track. So that's kind of what I think I'll bring. Thanks. For anyone already knowing that?
So this was a good presentation so far, but one thing that I'm aware of is the, particularly in my particular case at home, the standard solar installer is more than 5 kilowatts. So there's this untapped capacity for the export regular. Sorry, capacity is capping at 5. So if you consume more than 5, right, then you will unlock the inverter, which will give out more. So that's not going to be exported otherwise. I'm sitting at home, so I now have a 9 kilowatt system over 5. So there's 4 kilowatts in the middle of the day that the inverter won't produce. But if I consume that, then I will get that. So I'm just curious, is anyone looking to that export limitation for the 5? If they can self-consume, people can self-consume either by a resistive or a heat pump to get that potential out of there from solar. If you're limited to 5 kilowatts per phase, and every solar stands to launch that's not 5 kilowatts
For export.
So for that's right. Yes, that's not for export. So
Yeah.
you're actually you're not just simply just not generated. Your inverter's told to stop at 5, but it can
To export, it can still stop.
you can still self-consume. But I think when people are not at home, you haven't got a battery. It'll cap it. At that.
Yeah, so in Victoria, right, I can't speak for it, but I think some of the settings will be similar in other states. But yeah, we have a standard 5 kilowatt constraint on export. But then in specific cases where there might be high penetration solar or for other reasons where there are limitations, as part of the connection process, the household might be advised that they will be constrained further, even to 0 export.
Yeah.
We see more of that. We see more of that. We see more. So what we saw for a long time, and thanks to the SRES, the federal government program, we saw the 6.6 kilowatt, which is the panel size, which is the perfect over capacity of the panels to fit with a 5 kilowatt inverter, which was really around that grid constraint 5 kilowatt happening. That's not the case anymore. In Victoria, where 7.3 kilowatts is the average system size. Nationally, it's over 9 kilowatts. So that's today. So, and it's continuing to grow significantly over time. The payback period in the solar industry has always proven to be very capable of sitting customers down and explaining to them how this cash is going to roll in the door from the solar system. Predominantly, that discussion was predicated on the process of feed-in tariffs and a little bit of self-consumption. Obviously, with feed-in tariffs the way that they've fallen, and trends to continue to see that falling, that conversation has changed, and now it's talking around future-proofing and talking to customers around, well, you're going to have an EV one day, you're going to have a water heater, and absolutely, they're talking about that now. You're going to have a home battery. So solar is, as Dan was mentioning earlier, we're seeing this has been something that entering the electrification journey first with solar, and so they're making that investment in a considered way and thinking of larger system is best for them. Yeah. But in terms of the, so just one more point, again, just on the grid connection is probably dynamic exports or flexible exports. Lots of work happening in South Australia. Colleague Tim got to talk about in terms of being able to enable customers to have a greater than 5 kilowatt and a much smarter approach towards their grid constraints that are more managed to the grid. But it also means that it's in total right there.
So we also participated in that together with SAPM with that flexible exports review.
Yeah.
And that is something that is and enables you to sort of to go beyond the 5 kilowatt export when it's feasible to do that within that local grid. I think the whole concept of flexible or the flexibility around exports and what you then do with the energy that's generated locally should be looked at in a more holistic way, because the thing is, it's not just your local network that you're serving. It's also part of an integrated connected grid. So, and you've got considerations around the limits, but essentially, I think that the challenge is putting in place the infrastructure and the systems to enable it to have that flexibility. Because if you know what's happening in your local grid and in across the system, it's more intelligent. You can then enable a lot more energy to come into the market and not limit. But it does require that infrastructure step and market and sort of services change.
Yeah, there is capacity. I mean, there's a meter that sits there, for a meter that says, no, that's it. You have the amount. Just inverter tells you to cap it, but I can see it, but my solar is it caps at 5, and I've got nothing. can't do anything because there's a lot of capacity that could be used like that. Yeah, so some sort of future.
I think just to kind of build on that, I think there are a couple of things that the sector in general, so many, the AEMC, the AER, governing bodies or regulatory bodies, absolutely looking at, and what they're grappling with in a lot of ways is this concept of value, right? So, optimize at the behind the meter level initially, right? And self-consume as much as you can. And then what does that context look like at the circuit level or down from the transformer? What does that look like then at a substation level? The discussions around actually, by constraining your renewable energy export, are we not artificially, increasing the cost of renewable energy because you can flood the market with cheap renewable energy if it was unconstrained? Those conversations are absolutely happening, right?
Yeah.
What's going on though is how do you balance and make that transition in an equitable way so that, again, your unconstrained export, particularly if you're on like a single line and you're close to a transformer, downstream, your colleague or your neighbor isn't getting negatively impacted by that.
It's hard to just order fence and get extra electricity.
Well, it gets to peer-to-peer trading. But I don't, it'd be interesting, we can expand on this. Like, there's not as much regulatory barrier, I think, in our existing system as some incumbents actually maybe. So I think we're closer in.
It's a big really think about these times and really the DNP is already saying this is the cost to transfer energy. So it's just figuring out how aggregated you can actually trade it, want to trade it in the town. So,
Yeah.
So that's a follow-up question for me. And then how do you market it? How do you reckon you'd actually aim? Or like, how would you actually say, all right, here's a script for how you get demand response quality? Like, if we've seen this potential for it, how do you think you roll it out?
Do you go first?
Well, I'll give you.
Does anyone need to go to the APVI AGM? So it's starting now, if anybody's going to go to that. But I think the panel hopefully can stick around for a little bit longer. Yeah.
I was just going to say, from Solar Victoria's point of view, a couple of years ago, we launched VPP on batteries. We offered an additional $1,000 rebate for people to sign up through one of our approved VPPs. We opened it for 6 months. We extended it for another 6 months. We had 2,000 of these great value rebates available. With additional, the deals, I think we're offering an additional $1,000 off. So from the industry side, additional $1,000 off. So you're getting $5,000 off the purchase price at an average value of about $250 per year. And we got 480 customers. We probably had 2,000. So we did a lot of work on explaining to customers about how a VPP works, how valuable they are, how useful they can be, and what we learned through that. We're still actually doing some research, but what we learned from that is that it's that energy literacy, it's the customers having that go on that journey from getting solar, to getting a battery, to understanding what a VPP is. And it seemed to be a bridge too far. Yeah. And so the learned response of the solar industry was, if we try to go for broke and sell them this full package, we risk losing the sale altogether, and so they keep it simple. But what we do have is batteries that are VPP ready as part of our technology requirements, and we do have that ability, and we are creating this sort of the spillover to the incremental ability for people to electrify their households. And we obviously need to speed that up because we've got some targets to meet, but there is an opportunity for people to be able to sort of engage and get at their place.
So VPP ready work.
Well, we can give it a go, but I think our experience with only sort of 6 to 12 months ago, I'm saying that the market is not quite ready there for that yet. But we still need to keep going. And I think providing consumer offers that are enticing, not just financially but visually as well, is just as important to help people understand and to trust these solutions.
I think you in your talk you mentioned aggregators and need for aggregators. That's absolutely true. Because it's quite difficult to sort of put something out there that's a uniform set of across your fleet. Realistically, what you want is aggregation, but intelligent aggregation of that load, in tune with what the market's require. You kind of need it to be servicing the system and not just your local environment. Although the local environment, obviously, in some cases, does take precedent.
Yeah.
I mean, coming back to your question, I mean, is it a demand response that you want to set it for, or is it for a local service? I mean, this is where this holistic treatment of the issues that we face within the industry needs to come to the fore, because what is the first challenge that is met in or needs to be met in that local grid? I think Byron mentioned it, your voltages. So when you've got disparate sort of PV systems and loads within a local network, voltage becomes really difficult to manage. So, and that's probably an area where solar hot water heating can actually make a big difference, because if you had a simple regime around voltage, in other words, you could voltage.
Basically measure voltage out of that kind of water.
Yeah. I mean, and you can refine that in a way that still builds in the local requirements of that system, so you don't run out those sorts of things. But there's always going to be a little bit of play where you can actually make a difference. And so the demand response is one aspect, but and also catering for a local network service need or a quality supply need for your aids.
Yeah.
John, just a quick comment. We've actually seen some results from Postgrid looking at the local voltages as they come online during the day. And you're so right, there has to be done in a smart way, because it actually turns on, voltage goes down, and then it turns off, and then goes back up again. So it wasn't like a stable, smooth kind of way. So it has to be done in a smart way.
That's very true. That portion of response again, will turn all on at the same time.
Yes.
But I think I take a slightly different approach, in the sense that I think it's just making these devices, anything that has an inverter should be demand management enabled for a variety of scenarios. And the consumer doesn't need to be overly aware of what's happening, right? If the cell tower goes down and my phone automatically switches and does all this stuff in the background to provide reliable supply, I do not need to be aware at all of what is going on. Right? You can compensate the consumer. You can create contracts and engagement to say, you don't need to understand how a VPP works. Just here's a new system, or when you're ready to make that purchasing decision, we put the system in that has that capability. And if something happens where you don't have hot water when you need it, you'll either get compensated by a credit on your bill, or we'll figure something out. There's account management engagement that can happen there. I think that's the direction. 70% of consumers are not going to want to be overly engaged in this.
Please. In Europe and so forth, you're a lot more further advanced on winds than we are in Australia. First getting one and so forth.
Yeah, I spent
how much demand response how much demand response enabled products, or do you have much demand response capabilities in Denmark and Europe?
I think the situation, at least for Denmark, is quite different. Maybe I can talk a little bit about the conditions in Denmark. Is that 70% of houses, they have district heating. This is a large number. Majority of houses will be heated by the heat provided by the heating plants. The heating plants typically use combined heat and power, which they also kind of regulate the electricity price. And they also have other renewable technologies for heating, like solar heating will be mainly large scale solar collectors placed on the ground. So you can see that a lot of houses, they get heat from the district heating network. That means they are not they don't have option to switch to other technologies, because they have the binding with the district heating company. It provides not only hot water but also state heating. You cannot just this is not flexible for consumers. But in these days, there are actually some families, some houses, they have installed PV arrays on their roof, but mainly to provide electricity for the houses. At least as far as I know, there's no such a PV PV water heating system in Denmark. Not very many.
But what's the average price per kilowatt hour in Denmark?
For the electricity price, that is around 2 to 3 Danish kroner, around half, how many Austrian dollars would be if it divided by, it is the same if you divide it by 5.
Yes, okay.
I think
So
half,
2 to 3.
something like half the Austrian dollar, something like that. A little bit higher.
So that, I mean, that's not, we have, you know, 25%, 25% per kilowatt.
Yeah.
So,
So it's higher. Twice.
yeah, almost twice as much.
Of course, the electricity price, I see, is general for consumers, but for the network, the price for electricity changes every 5 minutes
Yeah.
or every hour. Depends on the wind turbines.
Yeah.
And the condition is that almost like more than half of the electricity in Denmark are produced by wind turbines. So you have a lot of excess electricity some hours of the year where you can get electricity like zero. There's also some days the price can be negative. You get paid if you consume electricity. So it's quite a different situation.
So back to the question though, is there a lot of products on offer where you can get demand side management technologies enabled or not?
No, not as far as I know. There are some companies starting to do this, like they give a solution only for tenants connected to the network. It's not PV, but they can be similar as in, but this network, but electricity, they can be charged at different time, controlled charging of the hot water tanks in the different families. But not so many cases mentioned.
I have a transition quick question about transitioning from gas to heat pumps, which we all talked about in the future. How do we prevent this term called death spiral, where so the gas consumers basically have to pay to maintain all the pipelines and the services and the maintenance? And as people go off gas, the same amount of money has to be drawn from less number of people. And the more people leave gas heat pumps, then they have to pay more to maintain this gas infrastructure. That's why also some people don't leave gas, because apparently they charge $1,000 to actually completely remove the pipelines and completely seal it off. So, especially for the Victoria case, how do we make sure that this doesn't happen to people who wants to stay on the gas and they end up paying?
Well, it's a live debate. And look, I don't know that to speak to authority, but I mean, the provision of gas service license is regulated, and the gas abolishment fees are also regulated. And we have recently in Victoria just set a fee. Someone remind me, it's about $200 or so. So we attempt to strike that balance between the actual, necessary costs of provisioning service with, providing some sort of disincentive consumers to stay in gas that had been. But in terms of as we see more customers move more and more and more, the customers move on the gas network, then who bears the cost of the effectively stranded asset? That's the line. That's still what's going.
I mean, I don't work for the government, so I can be a little bit. I have. Yeah.
really.
Okay, the Victorian gas substitution roadmap is great. The strides the Victorian government is taking towards getting us off of gas is groundbreaking in Australia. It's 100% supporting. I think there are systematic ways of looking at, pulling residential consumers, because we're talking about residential consumers, off of gas in a way that allows them, once a certain amount of consumers are connected to specific assets, the government can potentially come in and subsidize their transition over to electrification. You're talking about greenfield versus brownfield debate. The consumers are going to bear this cost anyway. So whether it's a tax, whether it's through our prices, what have you. One of the things that personal, comment here is that I don't think that there's a need for us to artificially prop up gas companies from an economic perspective. Like, burning stuff for energy is last century technology. We need to get away from that. We all know that. Burning things for energy is not part of the clean, climate that we need. The world is burning, right? We have climate objectives. We'll move towards that. We're not going to prop up gas networks artificially. There will be a space for them in industrial, use case, but otherwise, I think it's a systematic approach to pull us off of that supply of electricity or supply of energy for heating online. There are ways of managing it without unduly putting the burden on what we call vulnerable customers that might not be able to lean into that transition.
I'm mindful that we're shifting back. So, unless there's a burning question, by all means, catch up with me or Aaron, who will hang around, and maybe we'll